Morning. Good morning. Or should I say good afternoon? Good morning.
Morning, News.
Good morning. How you doing?
Good. How about you?
I'm awake.
Still on your first cup?
Well, I didn't quite make it to the coffee pot this morning, so I'll survive on water till afterwards. How you doing?
Well, I made my tea last night. I'm still on my first cup.
Oh, there you go. There you go. I didn't think of that. That would have been a smart move to do it early. So anything I need to do on this end other than just wait?
No, I don't think so. I did get a message from Gerard that he's traveling between two places and his flight was delayed, so he probably will not be here this morning.
Oh, okay. All right. Okay, sounds good. I got everything ready, I think. More than enough stuff sitting here, so I'm sure we'll have plenty to talk about.
Okay.
Looks like a few people are logging in.
Excellent.
Where are...
Santosh, are you there?
Hi, Jake. Good morning.
Morning, or afternoon, I guess, for you.
It's pretty much evening, 5 o'clock. So
Okay.
evening
Heading.
India time.
Okay.
Heading into evening, yeah.
Yeah. Well, I had. Here's a funny story. So, for the Tuesday one, I was very nervous, and didn't. I was like, oh, okay. What is it? What if the alarm goes off? And my wife had already said, she wasn't really happy about the alarm going off at 4 a.m. Twice in a week. And oh, okay. I'll get up right away. And I was a little nervous. And then I woke up once, and so the first time was all night, and then this time I was like, no, we did this, I'm good, we'll be fine. Woke up once on the night, and I look over, and the alarm clock is flashing 12 o'clock. 12 o'clock.
Oh no!
I was like, oh no! And it's still dark out. I have no idea what time it is. So I get up and rush to the bathroom, turn on my phone, like, okay, whew, it's only 3 o'clock.
Yeah. You have a power failure last night?
What's that?
You have a power failure last night?
I must have. I don't know.
Yeah.
It was the only thing that seemed to be affected, but I haven't been through the rest of the house to see if there were any other clocks that are off. So.
Yeah. Usually the kitchen,
It's usually the stove, one of the items.
Yeah.
The more difficult to set clocks that has the problem.
Yeah, it figures, yeah. So
The scheduled start is at 5, so we've got 5 more minutes to go. I see people are logging in.
Okay. And Noose, did you upload the slides as a PDF, or are we already looking at your desktop?
you're looking at my desktop.
Okay.
Why did you want them up? Did you want them uploaded or something?
No, either way. There's like 3 different ways you can show it. I was just curious which way you did it, because we haven't done one before.
I was just being lazy, so I went in. I did go in and edit a few things. I made a list of things we're going to talk about, and but yeah, you're looking at my desktop right now, and then I'll flip over to whatever I need to flip over to.
Perfect.
Yes.
Perfect.
So I think what.
And Santosh, I didn't see that we had any other registrations, so I didn't send any other reminders out this morning. Were there anyone else that I should invite?
No, I think whoever registered, they received the invitation. So I don't think there were any fresh registrations. And if there were, we would have sent the link.
Okay, and I've already got the recording started.
Yeah, I think that last one I did, the recording magically showed up the next day, so maybe there's some processing time or something.
Yeah, I think that was new. WebEx has made some changes, so that's my guess is that they switched it around.
Yeah.
Now it's not immediately available.
There was no notice of that, and so anyway, but yeah, it worked out. I think she was pretty happy. So.
And Santosh, Noose gets extra credit because he actually came into the office. Do this.
That's what I was going. I was going for the extra credit.
That's good, yeah. It's 4:30 there, right? 4:30 in the morning or 5?
Yeah, I'd be
Is it 4:30 in the morning? Is it 4:30 in the morning at Portland?
Santosh, did you ask a question there? I couldn't hear.
I was just inquiring as to what time it is at Portland right now. 4:30 in the morning?
I didn't hear it.
The audio is quite bad. Santosh's side.
Very echoey.
Yeah. And it looks like we have a few people who are not yet in on audio, so I'm gonna send them chat messages.
Can you hear me okay now?
Yes, that's much better.
Okay, I just changed headsets. So I was asking what time is it right now? 4:30 or 5 in the morning?
4:29.
4:29 a.m.
4:29 a.m. Wow.
Mm-hmm.
Bright and early.
It is.
And Santosh, do you see the chat window? The windows are arranged differently here.
Am I controlling that, Jake, or are you?
We both have it.
Okay. Because I just threw them over to the
I
other
can
box.
see it side by side. That's how I arranged it from my side. There's a if you click the I think there are 3 toggle views wherein you have a side by side view, a floating panel view, and the standard view, which is a video strip view. So what are you looking at?
I have 2 panels. I have the content with the video icons above and then all the participants over at the right, but I don't see the chat window, and that's how I managed all of the...
So if you click on the chat icon in the bottom panel, you see the chat on the right.
I have the chat window open, Jake. That doesn't affect you, does it?
No, but I did log in. We're both logged... Oh, there we go. I got it.
Okay.
All right. So let's see. We have a couple people who are in but not in on audio. So, Santosh, if you want to chat with them, do you know how to read that on the right? If they don't have audio, they don't have a little icon to the left of the name.
One second. I think I should look at the participants then. No. Right. Let me close the... Right. So several people have their mics muted.
Yeah. The microphone
started their... right. But some do have it open. Some have their videos on as well. You need to click the participants view to see this. So
yes, I have that open.
right.
And I see that Dr. Ratna Chatterjee is in the meeting, but to the left of their name, they don't have an icon to indicate how they're connected by audio, which means they're usually seeing the video but not the audio.
Okay. So should I ask them to re-log in then?
What I usually do is I'll just chat them directly and ask them if they need any help getting into the audio. And the way to get into it is to go into the audio menu and choose audio connection.
All right. So for those of you who couldn't, who are unable to hear us, probably go to the audio connection panel and select the model. Let me just type that as well.
I can also show that with a visual. Switch here. So I'm going to take over the screen for a sec. So if anyone is having trouble getting into the audio, you won't be able to hear me. But if we, so I'm going to show this.
Yeah, if you can't hear me.
Go into the audio connection. Okay. Okay. Noose, I'm passing the ball back to you.
Okay.
If you want to reshare your desktop.
All right. Everybody see it?
Yep, we're in. So Santosh, we're at 5 past. So we have chat from a couple people, at least from one, that they're still not able to hear. So Santosh, let's go ahead and address those by chat, and we'll go ahead and get started here. So my name is Jake Hopkins. I'm here in Portland, Oregon, and at the office here is Mr. Noose Hissam, our presenter this morning, and he knows a lot more about chemistry than I do. So he also agreed to get up early this morning to get started. So I'm going to ask him to go ahead and dive in.
Good morning, everyone. My name is Noose Hissam. I work here at Vernier Software and Technology. I did teach for 34 years, and I taught chemistry and physics during that time. And I've used Vernier equipment for 30 of those years, and so it's been kind of fun watching the progression of how the equipment has changed over the years, and it's also changed the way I've taught over the years, and hopefully I can share some of that with you today. Some of the thoughts were that some folks may not understand what we're doing, and so I just want to make sure it's clear that why we would use this equipment as opposed to some other option to teach the content that we're going to do. And I think you're going to see that the equipment we're about to use is going to open up some areas that you'll be able to explore with your students that you probably would have been much more challenging to do before this equipment was available. So hopefully I can share that with you and share some ideas about how to use the equipment effectively with your students. So that's the plan. And so that's why we use probeware, is that we're hoping that we can get in deeper and we can take some concepts that might be challenging to just talk about and explain and actually put it in the hands of you and your students. And that's what I'm going to try to do today is try to help you see that. What we're going to do is I was asked to particularly focus on spectroscopy And at Vernier, we have a couple of options for customers to use for spectroscopy. And I'm going to share some common experiments that I did when I was teaching. And these are experiments that are pretty common around the country that teachers do. And these are all experiments that come from our lab manuals that Vernier publishes. And so we're going to start with the Beer's Law experiment just to see how simply we can measure the concentration of a solution related to its absorbance. And then we're going to look at something more specific. We'll look at an equilibrium experiment that's commonly done, and how the Beer's Law aspect actually ties in to determining the equilibrium. And then finally, we'll look at a rate experiment, something that deals with kinetics. And in this case, it'll be a dye that changes color over time, and we can predict, what's going to happen. So why don't we get started here and see what kind of trouble we can get into. So here is Beer's Law. This is from I took this one from our Advanced Chemistry with Vernier lab manual. And what we're going to do here is we have the experiment, let me slide down here, uses copper sulfate in the advanced book. In our first year book, we have another book called Chemistry with Vernier. We use nickel sulfate. Nickel sulfate's a little greener, copper sulfate's a little bluer, and what the students are tasked to do is they're given an unknown solution, and I have some pre-made cuvettes here so that I wouldn't have all these solutions all over the counter, and one of them is marked unknown. And so this is a solution of nickel sulfate, and we don't know the concentration. So what the students are tasked to do is to determine the concentration of the nickel sulfate in the unknown using knowns to create a calibration curve from which they can then determine the concentration of the unknown. Now, we have two different ways we could do this experiment here at Vernier. Back when I first started teaching and using spectroscopy, I used to build these out of blocks of wood. This is a Vernier colorimeter, and this has 4 LEDs in here, and the LEDs are, of course, at different wavelengths. And what will happen is we can shine those different colors through our solutions and use the amount of light absorbed by one of the LEDs to determine, first off, to generate this calibration curve, and then to determine the concentration of an unknown. The other option that we here have at Vernier is we have a number of spectrophotometers. This is our most common one that's used in high schools. Many colleges are now using these too because of the cost. It's very, very affordable. And the advantage of this device is instead of being limited to 4 wavelengths like this one, this device measures the absorbance or emission spectra from 380 to 900 nanometers. So it's got a much wider range, and you can focus in on almost down to 1 nanometer if you want to. So I'm going to demonstrate both, but let me start with the colorimeter because this one for many schools is a much more affordable option, but like I said, there's some limitations, and let me share that with you right now so you can see what the limitations are. Jake, don't hesitate to interrupt me because you know me, I'll just keep on talking. So if there's something someone needs to see, let me know. So here's the colorimeter plugged in. There's a cuvette slot right here. There's a light source and a detector that line up in this orientation. And what I'm going to do is Jake showed you our Logger Pro software the other day, and wonderful software. Everything that I'm doing, we could do on Logger Pro. But we also have another piece of software called Graphical Analysis that we offer for free. And the advantage of this software is it will work with everything I think that Jake showed you the other day. But it also works with our newest sensors, which are ones that can be connected directly to a computer or a Chromebook, or they also have Bluetooth, so they can be connected to a phone or an iPad or something like that. So we have this version of our interfaces as well as the ones that plug in through an interface. So what I'm going to do is I'm going to take this device, and first thing I'm going to do is I'm going to simply look at the absorbances and try to decide. There's 4 wavelengths here. How do you decide which wavelength you want to use? And so, as a rough estimate, I'm going to simply put one of the green solutions, the nickel sulfate solutions, in, and I'm going to observe the absorbance of the solution when I put it in there and decide, like, for each wavelength, which one is the best one to use. And so I'm going to, I have the device set to the lowest wavelength, highest frequency LED right now. Let's put you can see the absorbance is very low. Let me put a sample of water in here. All of these solutions are aqueous, so they're made in water. I'm going to put that in here and just make sure that the device is reading 0 before I do anything, and it looks pretty good. Should it not be reading 0, there's a calibration option here. Some of you may be familiar with Spec 20s. In the old days, we used to have to go through a process to calibrate. Our sensors now, you push a button, and they automatically calibrate. And so that's what's happening. I'm going to take my darkest green solution, put it in here in place of the water, and just take a reading of the absorbance, and you can see on the screen that it's absorbing now around 0.37 absorbance units. If you're familiar with this, the absorbance units are relative units. They're not. They're unitless. I'm going to go ahead and switch it over to the next wavelength. So I'm just simply now push the button on here, and I've switched the wavelength to the next up wavelength, which is 470 nanometers. Absorbance is a little bit off, so I'm going to go ahead and recalibrate. As you can see, it takes no time almost to recalibrate. So now we can see it's going through the process and recalibrating the detector. And once that's done, I can put my sample in. The last one was 0.37. If I was having students do this, I would have them record these values so that they would have a record. You can see that at this wavelength, which is kind of a dark blue wavelength, it actually absorbs less. And I think, conceptually that makes sense. We have a green solution, but it might not for students. So you can go through all of the wavelengths. I just switched it over to 565 nanometers, and so let's see what it does. I'm going to make my solution is reading 0, as you can see on my screen, and so I don't need to recalibrate that one. Let's put the green solution in at that wavelength, and once again, a pretty low absorbance. Let me switch over to the last available wavelength, so in this case, the 635 nanometers, so now we're at kind of at the red end of the spectrum. Once again, let me check with the water and make sure that it's reading 0. Looks pretty good. Let me put the green solution in there, and you might find, even though you might think, well, that's pretty obvious, you may find for students it may not be as obvious that the green solution is actually absorbing a lot of light in the red end of the spectrum, and so this could verify that for them. So we know that that's the best of the choices I have on this device. That 635 nanometer wavelength is the best choice for this experiment, since it's absorbing the highest there. Now, the procedure for the experiment, like I said, I took this from our advanced chemistry book, and it walks through all the steps I'm going to go to demonstrate here. One of the things that might be a little different from what you might have saw with Jake the other day, some of you that may have seen that one, is that all of our sensors, when you plug them in, they automatically default to a time-based data collection mode. But in this case, if I go back, let me flip back to the experiment lab, you'll notice the graph says that this is absorbance versus concentration. There's no mention of time here. And so what we need is we need to be able to change the mode of data collection to a different mode. And so if we look at the software, right now it's set for time. Let me make the screen a little bit bigger for you all so that it might make it a little bit easier for you all to see this. This software has this option of enhancing the screen a little bit, so it's a little easier especially when you're doing presentations.
And
Jake,
that option that News just showed is extremely helpful if you're connected to a projector. because it makes everything, it doesn't just make everything bigger, it makes the proportions change also, so that the fonts are always a little larger, and it's just easier to read. It's not just when you need reading glasses, it's also very helpful as a presentation tool.
Does help when I forget my glasses, though, too, so that's good. I'm glad you mentioned that, Jake. So down here and at the bottom we have this option to change modes, and so I'm going to tap on that, and you can see that the default is time-based, but what I need is I need an option where I can put in a concentration, or I can put in a value if you're using a magnetic field sensor and you want to see how the magnetic field changes over distance, you would use this same mode. So I'm going to pick this event-based data collection, and what I'm going to do is this event, which will be the x-axis, this will be our concentration. This is where the concentration will go. And let's see if I can spell here. And, it's in moles per liter or molarity, your choice for the units. And so now I'm ready, and so I'll tap on Done. And you'll see that now I've got a data table, I have my graph, but I also have an extra button up here. And so I'm going to go ahead and start collecting data. Sometimes people will get a little excited at this point because I don't have anything in the colorimeter. It's like, it doesn't matter. The device is waiting for you. And so I'm going to take one of my knowns. If you look at my set of cuvettes here, what the students do in the experiment, by the way, if you're doing this in the classroom, you create the stock solution, and then the students dilute that solution to make these known concentrations. For the purpose of today's presentation, and when we go on the road, we take these kits with us just to make it easier and save time. But in your classroom, what the students would do is they would take the stock solution, and then you would tell them what the concentration was, and then what they would do is they would dilute that to the known, some kind of serial dilution, so they would know what the concentrations were. So what's happening is that this is really monitoring my colorimeter right now. If you look at the screen, there's the absorbance on the bottom right. You want to wait until that value stops changing, which looks like it's pretty good now. And at that point, when it stopped changing, I need to tell the system what that concentration is. So I'll tap on Keep. And it comes up and it says, okay, for that absorbance, what's the concentration? So in this case, that concentration was 0.32 molar, and that's one of the known concentrations that the students would create. And so now I can take that cuvette out. And the other neat thing I like about this mode of data collection is there's no urgency, right? It's going to wait for you until you click on Keep. So it's not like you're under a clock of any kind. So.
One of the things that I like to point out in this is that in this mode, we're collecting, so the software is measuring one number and you're physically typing in the other. So for the students to see that the table is being populated with two numbers over on the right and that you're seeing a point created on the left, that's something that's very obvious to people who have done a lot of data analysis, but to the students, always driving home that connection between the numeric representation of data and the graphical representation of the data is something that we know ties to the visual learning aspect of teaching. So they're making all of these connections and they're seeing all the data presented in multiple formats all at once. So in this type of experiment, we're going much slower because we might spend 45 minutes collecting 6 data points, but they're very accurate. So, sorry, go ahead, Nis.
No worries. Thanks, Jake. Thanks for chiming in. So what I've done while Jake was explaining, what I've done is I've put in all of the known concentrations. So now I've got, at least for the set I've got in front of me, the experiment itself has the students do five test tubes, but for this particular setup I've got 4 knowns. Now what happens is that you'll notice that if you do absorbance versus concentration, then the relationship between those two, according to Beer's law, is linear. So you can see it's a very nice straight line. And at that point, now that I've done all of the knowns, I'm finished collecting data and plotting it. So I'm going to click on Stop. A couple of questions that usually come up at this point is, what if a student makes a mistake? The way our sensors work and our software works, not so much the sensors, but the software, is any data that is entered by a student. So these numbers here in the table that I entered, if I made a mistake, I can edit those. So I can go in there and change that value if I made a mistake. What you cannot do is you cannot change a value collected by a sensor. So that makes it more difficult for students to massage the data and make the graph look the way they want it to look. So you cannot change these values. If I try to do anything with that data, I can't change that. So anyway, getting back to the experiment, what we want is we want a calibration curve. So the software makes it very easy to explore options for fitting curves. And so I can pick this option, and this little icon at the bottom lets me change that has different tools for analysis. And so I'm going to put a little curve fit on here. Linear curve fit is the most common one. But you have many options, and we are going to actually explore some other ones here with another experiment that I have planned for today. So I'm going to stick with the linear option for now. I'm going to tap on apply. We're kind of done with the data table, and because of this, I have this presentation mode so large, I'm going to get rid of the data table temporarily, so I'm going to just switch over to a graph. And so now that makes it a little easier for you all to see. Here is the regression equation for the line that I just plotted, and here is the slope and y-intercept. You can see that it's a pretty linear relationship. I have 3/9 correlation, so that's pretty good. So this is showing me how the relationship of absorbance to concentration for this set of known samples. So if you remember, I started out the discussion, the students are presented with this solution that's marked as unknown. And the question is, well, what's the concentration? And so what you would do at this point is you would put that into the colorimeter. If you look down here at the meter, that's live. That meter is running the whole time. So the software is monitoring the absorbance of the solution. So what I can do is I can take this value, and now it depends on your students and what you're trying how you're trying to get them to understand this. Years ago, we would print this out. We would take this number, 0.35. We would go to the y-axis and draw a line with a ruler. We can do that a little more elegantly now within the software. We can tell the software to interpolate the data for us, and so we can go in there and we can do basically the same thing as we used to do with a ruler, but I can move this to the point where I've got the absorbance that I'm reading on my meter on this little dial here, get it as close as possible, and then there's my concentration listed down here. When I taught, I didn't like this mode, and not only did I not like it, I didn't tell the students. Sometimes they would find it, sometimes they wouldn't. For most of my students, I would say take this regression line. All of you have taken algebra. The y value is going to be the absorbance because that's what's plotted on the y-axis. The x value is going to be the concentration because that's what's plotted on the x-axis. Plug in the values for slope and y-intercept and solve for the concentration. You know the absorbance, 0.35, that goes here. You know the slope and the y-intercept. Students with algebra skills should have very little trouble solving that equation, and that would be the preferred method, I think, to determine the concentration of the unknown solution. I'm going to pause at this point. Jake, is there any questions anyone have about how this was worked out?
I haven't seen any chat questions come in about the content of the Beer's Law, and I realized that I didn't invite everyone to do that. So we are going to open up the mics at the end if anybody wants to post any questions that way. But in the meantime, if you want to send them in by chat, I'll collect them all, and we'll pause a few times throughout, and we will definitely answer any and all questions that everyone posts. We've gone through Beer's Law one way here, and I think Noose is prepping to switch to another mode here. But if you have any questions about the content, this is one of the most popular activities from the Chemistry with Vernier lab book. This one is also mentioned in the IB. Oh, there it is. In the IB correlations, and if you go to vernier.com/IB, you'll see all the information about different lab books and how we support the International Baccalaureate curriculum and how each activity from each book is aligned. News, I did want to mention, if you want to pop over, since you're in presenter mode there, if you go to the table, just pull up the Vernier.com/IB page. I know that a lot of your schools cover the International Baccalaureate curriculum, and on our website, so yeah, just /IB, you can see the correlations between all the lab books that we've produced and the labs that are recommended. But we also do this for, you need the www because you're in the office news. It's a subdomain because of the network routing.
Right,
so
right.
Just the correlations between International Baccalaureate and all of our books. So if we go into chemistry there, we can see how each of the topics that are mentioned in International Baccalaureate and how those correlate to specific labs out of our lab books. And go ahead and choose one of them there. And if you follow those links, that will show you the kind of the sample of that particular activity from that book. In this case, it's from the Advanced Chemistry lab book. So we sell these lab books that have the step-by-step instructions. And the other thing that they include is the Microsoft Word files. So like Noose mentioned, he would do the lab a little differently. And that's one of the fun parts about working with teachers is that teaching is not an exact science. There's also some art involved and some creativity and doing it your own way and making your own. So if you do the lab as written, these are written by teachers for teachers. They work well as done. But then a lot of people like to tweak the graph or tweak the lesson, make it a little bit more yours. So you have the Word files, you can edit it and go ahead and make any changes you like and do your own version of the lab. So, Noose, we had a question there of why isn't the graph passing through the origin?
Why isn't the graph passing through the origin? There's going to be, well, first off, I don't even see the origin here, so why don't we take a look at that? The y-intercept is pretty low, but let's go ahead and adjust the graph so we can see what the origin looks like. In the Graph Tools option, I can go there and set my axes so that I can see what's going on at the origin. So let me do that. Let me change these values so we can see how close to the origin we are. Like any data collection option here, there's certainly some error associated with this, and so that's part of the reason. You would expect that at the concentration of 0, the absorbance would be 0. The other thing to think about is how far off are we? If you look at this value, the at of absorbance of 0, this is reading a concentration. Let's go ahead and read that of 0.03 or 0.04, maybe if you do a little rounding there of molarity, moles per liter, and so that's extremely low and probably well within the error of the device. The device has certain intrinsic error, and we're probably pushing the limit on the ability of the device to meet that error. But that's a good question. I mean, it's certainly one that I hope the students ask is why, if the absorbance is 0, shouldn't the concentration be 0? And part of it is going to be the error built into the experiment, built into the device. Good question. Any other?
And the next question is actually a perfect segue into the next section of the differences. What are the differences between a colorimeter and a spectrometer?
Oh, who did that? Was that Jake? Did you put that up there?
No, I didn't. That really did come in from someone else.
That was fantastic.
Would I ever do that?
Well, I don't know. I wouldn't put it past you. That very good question, and thank you for whoever asked that question. Advantages and disadvantages. I mean, probably the number one advantage that a lot of people look to for this device is the cost. This one is considerably cheaper than a spectrophotometer. But let's look at the spectrophotometer so we can see what the advantages are, and then we can talk a little bit about what you can do to even work on that cost issue. I actually wrote an article, and I'm making presentations about how to to maybe just get one of these and still have a classroom set of these and do the same experiment effectively. So let's take a look at that. What I'm going to do is I'm going to switch gears slightly, and what I'm going to do is I'm going to do another experiment that takes advantage of Beer's law but also uses the concept of equilibrium. And so you may or may not, some of you may be familiar with this one. I have a little movie here. Let me find it for you. This is solution, the vial contains a solution of iron thiocyanate, iron 3 ion. That's why it has a little bit of a yellow tinge to it. And the person here is about to add some potassium thiocyanate to it. So let me just do that for you so you can kind of see. It's not very practical for me to do this, and I don't think my employer would like it if I spilled this here in this nice office. So I'm showing you the video. You mix these two together, and the complex that's formed between the iron and the thiocyanate ion is this reddish-orange substance. And so, not very unusual to use that experiment with a colorimeter or spectrophotometer. And I will admit that this experiment can be done with the colorimeter, but why would you choose it? The question was, why would I want this device? And so let's take a look at that and see how that works. Let me review this just for a split second here. To understand this, to determine the equilibrium constant, the students need to be able to determine the concentration of these species in the equilibrium expression. The only thing in here that has significant color is the numerator. And so that's what we're going to be measuring with our spectrophotometer, and then we'll use an ICE table or some method of calculating from known concentrations what the concentrations of these things are at equilibrium. And so that's the basics of this. And the nice thing about this activity is it reinforces the concept of setting up an equilibrium expression very, very, very well. And so let me demonstrate that for you. Here's the idea. The way the experiment works, and once again, I've got some prepared cuvettes. I apologize that I don't have the actual chemicals, but I would be kind of in trouble if I spilled them over here. I have some prepared cuvettes that are of known concentrations, and let me bring over I was just pulling up the table here. These are known concentrations. And the first part of the experiment, what the students are tasked to do in the pre-lab, let me bring the lab experiment up here. In the pre-lab, the students are tasked with determining the concentration of the iron thiocyanate. So that's part of the pre-lab experiment. If they start with known concentrations, how do you do that? So they're basically, what they're doing is they're developing knowns for the calibration plot when it comes to Beer's law. But we're going to spectrophotometer so you guys. And then I've got a number of test containers here, marked A, B, and C. These are of unknown concentration. And what we do is use these to actually calculate the equilibrium. So let me show you how. The spectrum is here.
Your audio is starting to get a little choppy.
I'm on the phone, so I don't know what else to do.
Yeah, I'm not sure, and it stopped there as soon as you paused and then started back in. It got much more clear. So okay.
I talk
go ahead.
Too much? I might have been talking too much.
No, I don't think so. I don't think you've filled it up or anything.
Yeah. So I've got the SpectraViz plugged into my computer. We have a special free piece of software, new, that we call spectral analysis, and let me fire that up so you guys can see it. And we're very proud of this software. The reason is that it takes a different approach to, and we feel that way about graphical analysis too, it takes a different approach to presenting the experiments to the students. Logger Pro is wonderful, and Logger Pro does everything, but there's some advantages and disadvantages to that. If your primary interest is spectroscopy, we feel like this software is really starting, this spectral analysis software is really starting to become something that teachers are enjoying. And so what we're going to do is we're going to basically build the Beer's law plot that we did before using the spectrometer, and then and we're going to use that plot to determine the concentrations of these unknown mixtures of iron 3 and thiocyanate. So let me show you how we're going to do that. You notice that in this software, there's actually an option to do Beer's Law. Now, you'll notice, I know some of you IB teachers like to do it in terms of transmittance, and we do have that option built in, but as you may be aware, that the transmittance against concentration is not linear, so you would have to do some massaging of your data to plot a log plot to get the absorbance plot. So I'm going to stick. I don't want to. We only have a limited amount of time, and I don't want to drag that out. But it absolutely could be done, and that's why percent transmittance is here. Is because so many teachers would prefer to do it that way. In our AP chemistry manual, the very first experiment that the student teachers do is the concentration of blue food dye in sports drinks, and they do it starting with percent transmittance because conceptually that makes more sense. What we see in the colors that come through solutions, though, that's transmitted light, so it makes sense, but it's a little more advanced topic. So I'm not gonna belabor that today. I'm going to stick with a little bit simpler and stick with absorbance. So I'm going to use, similar to the last time, I'm going to use Beer's Law plot here, and I want you to see what happens when I choose that. What happens, of course, and I've been talking on purpose to kind of to kill a little bit of time here, this device has numerous light sources in it, and those light sources need to be warmed up. And so depending on how soon you click that button, it will walk you through up to about 90 seconds of warm-up. But you'll notice that there is an option to skip. So if during the class period students need to switch modes or they need to do another experiment, you can skip that warm-up mode after it's already been plugged in for a while. Now, here's what I wanted to point out. I've got a blank in here. So the blank, in this experiment, the blank is not water. The blank is iron 3 solution, because the iron 3 solution tends to be slightly yellow, and so we prefer to use iron 3 for the blank. I'm going to take one of my known solutions. It doesn't matter. I'm going to take one of my red solutions, because now notice the difference here. The last time I walked through the wavelengths to find the best wavelength. This time I'm going to take a solution, I'm going to put it into the SpectraViz, and it's going to measure a full spectrum of the absorbance. So from 380 nanometers to 900 nanometers. I mean, the infrared is not important here, but what you notice here is that we're getting an absorbance, high absorbance here that's kind of in the middle somewhere. And what's interesting about that is that you'll notice that that number, in my case 424 nanometers, that's not any of these wavelengths that are on the colorimeter. Now, not to say that you couldn't use the colorimeter, but you would have to pick the closest wavelength, and so you would be on one of the shoulders in order to do that. So if you pick the 470 nanometer LED, or if you pick the 565 nanometer LED, you're going to be on one of the shoulders. You're not going to be at the optimal wavelength. So with the earlier question was what's the difference? This experiment, studies like this where you want to be able to pick a specific wavelength to do your study, this device allows you to do that with a wide range of choices. So once I've decided the wavelength I like, then I click on...
And one other thing I like to point out is that, so with the colorimeter, you only have 4 wavelengths, and this spectrometer is also what's called an array spectrometer. So if you've used a Spec 20 at university, even then you typically need to choose a specific wavelength before you run the experiment. And because we're collecting that whole visible spectrum in less than a second, you're able to get a lot more data in a much shorter amount of time. So the students can look at a visual representation of the data like this and then choose which wavelength they want to run the experiment at.
Well, and you bring up a painful point there, Jake. Speaking from Spec 20 memories. The other thing is every time you pick a wavelength on a Spec 20, you have to recalibrate. And so what we just did when I put that blank in there earlier is I calibrated the array at one time. So do not have to, even if now that I'm choosing a wavelength, I don't have to recalibrate. It's already been done. So here we go. Let's go ahead and hit done because I've chosen the wavelength that I like. And notice it goes right to that mode that we were looking at before. And so it's a similar experiment, but the big thing is it allows you to choose a wavelength. After that, it's really pretty much the same. So we're going to start collecting data. You can see the screen looks similar. I like this little guy, this little mini graph, because you can actually visually see what's happening to the spectrum as you change the cuvette. So let me put the value in here for this first cuvette. This comes from the pre-lab that the students did. And so in the pre-lab, the students determined that first one has a concentration of 1.6 times 10 to the minus 4 molar. So they would type that in to the software, very similar to like the way you do it on a calculator using the E key for exponential. And so I'll keep that point. It plotted it here on the graph. Oh, let me get this also has presentation mode, so I can make it a little easier for you all to see what I'm doing. Now, what happens is I switch to presentation mode. Now, this guy is could be a little bit annoying. If it gets in your way, you can get rid of it. But if you want to see it again, if you change your mind and say, oh, I really want to see what's going on, you can turn it back on and off again. So, depending on what you're doing, that might be something that we might have to adjust. Let me get that guy out of there. Notice it's continuously measuring. I just put another known solution in. So you can see this is very familiar to what we just did a few minutes ago. Meter is live. And so now I'll wait till it stabilizes and then tap on keep. And then let's go get that value from the pre-lab. So 1.2 times 10 to the minus 4. And you can see same rules apply. It only allows you to change values that you put in. So you're not allowed to change values that are collected by the spectrum. 8 times 10 to the minus 5. Let's keep that value. And one more. Wait for that absorbance value to stop changing, and then keep. And that one is 4 times 10 to the minus 5. Okay, and so I'm done. And once again, but notice, by the way, notice what's happening. This is the original. If I'm looking at the insert, this is the original that I used to select my wavelength. This is the cuvette that's in there right now, the red line. So it kind of gives a very nice visual, what's going on? What's this thing measuring? It's measuring how much light is coming through. And you can see it's, with a darker solution, less light is coming through. With the lighter solutions, more light is coming through. So if more light is coming through, less light is being absorbed. This is a tough concept for students to understand what is the difference between absorbance and transmittance. I'm going to get this guy out of the way right now because I want to do analysis. And so I just close that window. What I'm going to do here is I've done my knowns, so I'm going to stop collecting data, and I'm going to do the same thing I did before. I'm going to fit a curve. So it's very I wanted you to see Beer's law 2 different ways, and so this is why I designed this. The red solutions are, especially these that I use for the road, they tend to be affected by room lights a lot, so I don't get quite as good correlation. Not too bad. I got 2 nines correlation here instead of 3 nines, and you can see my y-intercept is pretty low, but not beautiful. But let me get this out of the way here. And so now what I can do is I can do the same thing as I did before. If we go back to the experiment, what we want is we want to know what the concentration of the iron thiocyanate is at equilibrium. And so we've got these unknown solutions that the students set up. They're labeled A, B, and C. And what the students would do is they would put that in in to the spectroviz, and the same rule applies as with the colorimeter. I put it in there, I read the absorbance, and then what the students do is put that absorbance value into the regression equation, and using the slope and y-intercept, determine the concentration of the numerator, okay, of this equilibrium expression. Now, as you may remember, when you set up an ICE table for this, initial change and equilibrium table, the amount of iron thiocyanate that's produced in the product, that's going to be minus X, or, well, it's going to be plus X, but the amount of concentration of iron and thiocyanate at equilibrium will then be that value, the initial value you started with, which was given to the students. So students knew that this is what the concentration were of the solutions when they started. So they've got that minus the concentration of the iron thiocyanate that was at equilibrium, which they got from the graph. So they've got their three concentrations, put those into the equilibrium expression, and solve for an equilibrium constant. And if it's an equilibrium constant, theoretically, it should come out to be the same value every single time. You'll find that we find that it's very difficult to do that. More often than not, you're within about 10%. And so it's not perfect, but you do get the idea of setting up the expression using real data, and so there's a lot of good experience for the students as to how these sorts of things are measured and where do these magic numbers that you see in books come from. This is an application of Beer's law for a specific concept, in this case for teaching equilibrium. Are there any questions from anybody?
Yeah, we had one question. We answered it mostly there by chat, but it might be valuable to kind of share it with others. The question about the concentrated liquids. The concentrated liquids can't be used in the colorimeter cuvette, and could that be changed? So some of the cuvette options there.
Okay. So when you buy either the SpectraViz or the colorimeter, we supply them with 15 plastic cuvettes. And we also sell these in boxes of 100, so if you need to get more for your class. But you're not limited to these. This is a standard cuvette size, so it's a 1 centimeter light path cuvette. As long as you get cuvettes that are that size, anything will work in this cuvette slot. So if, for example, you mentioned you want to use a higher concentration, or what will kill these cuvettes in about a second is acetone. If you put acetone in these, they'll melt in your hand. I mean, the polystyrene just won't stand up to it. So you might use glass cuvettes, and glass cuvettes will stand up to acetone. The problem with glass cuvettes is, with the SpectraViz, it's not an issue because it only measures down to 380 nanometers. But with a UV, we sell UV spectrometers. Glass doesn't work, and so then you need to use a quartz cuvette. And so for quartz cuvettes, the cost is considerably higher, but they will stand up to acetone. They are opaque to ultraviolet, and so you won't have the issue of the glass absorbing some of the wavelengths. So as you might imagine, as you move up through the different types of cuvettes I discussed, the cost goes up. But yes, you can do that. I would be very careful with higher concentrations getting them on the devices, or with organic solvents. This cuvette slot here will not stand up to acetone either. So if you spill it, you could damage your light path. We also sell. Most of our cuvettes have two sides clear and two sides fluted. But we do sell, with our fluorescence spectrometer, we do sell cuvettes that are all sides are clear. And even though this device can do fluorescence, you could use those cuvettes in this. Another advantage of the SpectraViz is that not only can it do absorbance like you've seen me do here, it can also do emission spectra. I don't know that we have time, but I do have some tubes here. By simply plugging in a fiber into the cuvette slot, which is sold separately because not everybody needs the fiber, but by plugging in a fiber, I can now take advantage of the detector in here, and I can shine light into that system, and then I can look at the absorbance spectrum. So since I plugged it in, I might as well do one real quick here so that you guys can see what I'm talking about. So let me do a quick emission spectrum here of these room lights. It's this very same device. So another advantage of this device is that I can plug in a fiber. I think the fiber is around $70 US. And then what I can do is now what I'm looking at, what you're looking at here, is the emission spectra of the lights in this room. And this one right here, this peak right here is a mercury peak. And so the same device does require a small accessory, but this is very good for when you're teaching in atomic theory and chemistry, or maybe in physics also. The other
emissions
thing
is the only one that we use much in physics. That's in physics. That's sort of the fun mode. Be able to look around and look at. We have the spectrum tubes. You can look at different options, and then the one that Noose just said there is one that's often interesting. Of is there mercury in this light? So you can always, if you know the wavelength, you can look for that, or you can also compare it to some known samples and see what emission spectra you're seeing and what specific elements are represented.
Yeah, one of I love this device when I was teaching. I didn't have a ton of them because they do cost $400 a piece, but when I was teaching, because I was able to demonstrate things that I'd only been able to talk about until this device came up. And this is another one that we are very, very happy with the software now. The device, we've had a number of years that can do what I'm about to demonstrate, but the software is just amazing what it does. This is a cuvette of fluorescein. So this is the material that's in the ink in highlighter pens and things like that. I'm about to collect the absorbance spectrum for this. So what you're seeing on the screen here is the absorbance of this fluorescein. So this stuff is absorbing. Let me stop collecting data. It's absorbing at about 488 nanometers. Now, what I'm about to do is take advantage of the third mode of operation of the spectrovis, and that is the fluorescence mode. I'm going to go ahead and switch modes from absorbance to fluorescence. I have to keep in mind that 488 because what this device does is it has two excitation LEDs, and I'm tempted to turn the lights off in here, but I don't know what things will look like if I turn the lights off. I think you guys can see it glowing. If I slide down here, you'll see that it has the option of switching between 405 and 500 nanometers. Let me switch it back to 405 just for dramatic effect here. I'm going to change it to that mode, and then what I'm going to do is I'm going to collect some fluorescence spectrum at 405 nanometers. So let me do that real quickly. And what I want you to notice is that let me stop collecting data here. Is that the fluorescein was absorbing at 488, and then something's happening here. Well, what's happening here, honestly, is it says 515. It might be emitting that. It might also be reflecting some of the light. Let me go switch it one more time to the other wavelength. So instead of the 405 nanometer excitation LED, and I'll explain what this means here when I get this one going, switch it over, and let's take a look at the fluorescence spectrum with that one, and you can see that this little pink one here was the 405 nanometer. Now look at this red one. It's actually peaked out. It's flattened and peaked out. So if I hold this up, I want you to be able to see this. If you notice, and I'll hold my hand there so you can see it glowing. The stuff, if you look at the original, let me bring this out. If I bring out the original, it's yellowish in color, but if I put it in there, you can see it's glowing green. And so what's happening here is there are two LEDs in here that are perpendicular to the light path, and one of them is a 405 nanometer LED, which is very, very purple, and the other one is a 500 nanometer LED, and that's kind of a greenish color. But I'm exciting this with the 500 nanometer LED, and notice that I'm getting a ton of light out of this. So what does this mean when you're for students? Well, it means that you're taking energy into this molecule, and then that energy is being re-emitted at a higher wavelength, a lower energy, but it's fluorescing now. So how does fluorescence work? So there's some really cool applications of this. The other one that we find that is very much fun to do is chlorophyll. If I take This is some chlorophyll that I pulled out of spinach the other day for a workshop I was doing. If I take that same chlorophyll and do pretty much the same experiment, I'm going to take the chlorophyll and put it in to the spectrometer. I'm going to fill the cuvette up a little extra, and hopefully I won't spill anything in here because I'll probably get in trouble if I do. And let me do the same thing. I'm going to take the chlorophyll and stick it in here, and going to do that same experiment with the chlorophyll. This is something that's super easy to do. Any green plant will probably do this, but I know spinach works extremely well. Let me collect the absorbance spectrum for this, and once again, since I've been doing this a lot, I can wait. You have to wait 20 seconds before you get the option to skip, but I'm going to skip the absorbance. Skip the calibration mode here, and should give it to me here any second. There it goes, and now I'll calibrate the thing. This one is kind of, first time I saw this when I was teaching, it kind of blew me away. So I've got the chlorophyll in there. Let me collect the absorbance spectrum. So this is chlorophyll A and B probably. And you'll notice that there is a strong absorbance down here around 420 nanometers. So I'm going to switch over to the fluorescence mode, and I'm going to use the 405 nanometer LED to excite it, because since that's closest to that absorbance wavelength. This is called, for those of you that might be familiar with this or not, this is called Stokes shift. And so now what I'm going to do is I'm going to excite this thing, and so notice this little bump right here. Not a whole lot. Okay, so let's try the other LED. Let's switch over to the 500 nanometer LED, and let's excite it with that one and see what happens. I love the ability to just modify this so easily. So I'm going to, now the other thing some of you may have noticed, I have a right axis on this one. So I can turn off or on whatever I want to plot on the right axis. So let's look at the 500 nanometer excitation, and you'll notice I was hitting it with 500 nanometers of light. That's going to be this peak. But look at this. It's emitting at 685 nanometers, and this is really hard for you to see with the lights on in the room. This thing is actually glowing red. It's chlorophyll, but in here it's glowing red. And that, to me, it's taking light in at a certain wavelength and emitting light out at a higher wavelength, but which also represents lower energy. What a great thing that we can do now that we just didn't have before. And this one device. So, question earlier, like why would I use this device? Well, it opens up a lot of concepts that you can demonstrate that you just couldn't demonstrate before. Now, Jake, I'm running low on time, but I do have kinetics sitting here ready to go. Is there an interest in looking at crystal violet kinetics? It's this experiment right there. Do you want me to do it?
Well, if anyone would like to see that, go ahead and chime in on chat. I was just going to point out a couple of things there. The spectrometer, when we first started doing spectroscopy, we thought this was going to be something that was only done at universities because of cost. But now that the spectrometers have both gotten better and less expensive, we've actually seen more and more adoptions at high schools because it is just much more versatile than a colorimeter. We've had a version of a colorimeter for 25 years, and we've had spectrometers for less than 10. But in those 10 years, the spectrometers have gotten better and better and more affordable. So a lot of times it's just we'll start with one as a demonstration and have the students each have one colorimeter at each station. But then they'll a lot of times after that we'll expand it out and say, oh, I'd really like to do more of these experiments and expand out with their use of spectroscopy. So we do have a question here, Noose, about can solutions at varied temperatures be used in the cuvette to determine the absorbance?
Yes. That's the thing that's on the screen right now, related to what Jake was just saying, is an article I wrote that's on our website, and it's called Discover the Wavelength. And this one does demonstrate how to have one of these in your classroom and then a class set of colorimeters and have the students experience pretty much the same experience as having a class set of these. I don't want to discourage you from buying these necessarily, but some people's budgets are limited. And that's what you might find. So as far as temperature, so seeing if you want to do a Arrhenius equation and you want to do how does temperature affect the rate of reaction. The way that we have one experiment in our Arrhenius experiment. Let me stop talking for a second because I think getting some feedback or something.
Yeah, I think I know what it is.
We have an experiment in which the students combine solutions of different temperatures, and they try to build the activation energy for the reaction using the Arrhenius expression. That one, though, they basically take their solutions. Let me show you how similar to this. You take your solutions, put them in pipettes, and then what you do is you put these in water baths and you warm them up in a water bath, and then at different temperatures you combine them. There is no water jacketed way to keep the temperature constant in here. So the temperature is going to change once you take it out of the water bath. We have had some customers, we sell a very, very small temperature probe. It's called a surface temperature probe. And we've had some customers with some luck being able to sneak the temperature probe into a cuvette. And the idea is this temperature probe is teeny weeny. Let me see if I can bring one up here on the screen so you can see it. And what they've been able to do is they've been able to slide the temperature probe. You can see how small this bit right here is. Slide that in and keep it out of the light path. And then they've been able to do experiments where they can directly measure the temperature of the experiment and relate it to the equilibrium constant. Or, pardon me, not the equilibrium constant, the rate constant. The only thing about this guy here, if you're thinking about trying to do that, is this baby is only good for aqueous solutions. Don't think at all about putting this in any kind of organic solvents. And I think the highest concentration we recommend is 1 molar. So you don't want to do anything that's higher than that. So, okay.
Noose, we also had a question of can spectrometers be used to determine the activation energy?
Yes. Let me show you that experiment. It's in. I didn't memorize the numbers. I think it's 35 in our book. Let me bring it up here so you guys can see it. It's in the advanced chemistry book, and I think it's the last experiment. Let me call it up here. Where's advanced chemistry?
35 in chemistry.
Yeah, I was just bring up the PDF file. Here it is. So here it is. And so similar. That's what I was just describing. What the students do, you use crystal violet. This is the one I was going to demonstrate today. So this is crystal violet. This is sodium hydroxide. You put these in various temperature baths. So let me slide down so you can kind of see some bit of that. So you put it in various temperature baths. I guess there's nowhere here to really. Here we go. And then what you do is you determine the rate constant from each run of these. That's the demo I was going to do. Let me show you the teacher page so you can at least see what the final output looks like. Jake had described earlier that when you buy our books, you also get all the teacher pages with sample data and things like that. So here's what a plot looks like of the log of the absorbance versus time, because this reaction of crystal violet with sodium hydroxide is first order. So you would plot the integrated rate law for this. You would plot the logarithm of the absorbance. When you do that, you get different rate constants at different temperatures, of course. And so then what you do is you plot those temperatures, the absolute temperatures, the inverse of those, versus the log of the rate constant, and then the slope of the line will be related to the activation energy. It's not the activation energy, but it is related to it. So you have to do a little massaging of the data to determine the actual value of the activation energy. But if you own our book, experiment number 35 in advanced chemistry, pardon me, you do determine the activation energy of this reaction. Okay. Any other questions?
Couple questions there about the surface temperature sensor, but I am answering those on chat. Let's see, activation energy. Question about the plot of not being of absorbance versus wavelength. I guess I'm not understanding. When you integrate that temperature sensor into the setup news, so the temperature sensor won't work for the surface temperature. You wouldn't necessarily be plotting it. You'd be using it more as a control, or
well, it depends on the experiment. With that experiment that I was just describing, you would not be plotting the temperatures. You would be measuring the temperature of the reactants before you mix them. It's not impossible. Like I said, if you use a surface temperature probe, as long as you arrange it so that the sensor, which is very small, this little bit, is out of the way of the light path, you could slide it down into the cuvette to measure the temperature as the reaction is occurring and maybe get an average value. That's not the way that we wrote the experiment, but I do know some colleges do that. They measure the temperature as the reaction is occurring to get a more accurate reading of what's happening.
Would you still plot temperature? So would you plot then temperature versus absorbance, or would you do absorbance versus wavelength and then do multiple trials at multiple temperatures?
Yeah. The temperature would only be recorded for each run. So if you look at your data table, you would just record the temperature for each run. You're not plotting anything there. What happens is you're running this, in our experiment, you run the very same experiment 4 times, each time where the reactants are at different temperatures. So you have 4 sets of these. So you'd have one set would be sitting in one water bath, another set would be sitting in another water bath, and you would be running these separately. Now, in our experiment, what you do is measure the temperature of the water bath, and that's as good as we do. Like I said, there's some colleges, what they do is they take the surface temperature probe, stick it down in the cuvette, and they measure the temperature in the cuvette while the reaction is occurring. I think they feel that gives them better results. I think at my level, at high school level, just being able to relate the temperature to a rate constant was all I was after. So I didn't feel the need to be able to measure the temperature in the cuvette. But you could do that. You're not plotting that temperature directly. This last graph here, what's happening here in this graph is you're manually plotting this data. This data is not plotted from data collected directly by a sensor. You've determined the rate constant. So here are the 4 plots. This is data plotted. So this graph you're looking at right now is calculated columns that have been done on absorbance to plot these lines. So that is being done from data that was collected with a spectrometer. But this graph down here is a manually plotted graph. So this one, you've taken your rate constant and you've taken your temperatures. Now with all of our software, you can create calculated columns. So you put in the rate constant that you determined in the first part. So notice there's a K value in each one of these. You put that in a column manually and then have the software calculate the log of it. And then the same with the temperatures. You put the temperatures that you recorded, here are the temperatures. You put those in a column. They have to be absolute, so you have to change them to Kelvin, and then you also have to take the inverse. And so all of that can be done with a calculated column. That's a whole workshop in itself, so we'll save that for another time. But you can do all of that with our software. But in this experiment, you do not measure the temperature directly, nor do you plot the temperature from the sensor on a graph. Yeah.
Okay, so it looked like that one answered it. So we are a little bit over time. If anybody else has any questions here, go ahead and post them via chat, and Noose and I will stay on for another couple of minutes. But that's Noose is always ready to do their experiment there. He's got at least 2 or 3 more on the table there, where you never know how fast it might go.
Crystal Violet right here.
We'll stay on to answer any other questions. And if not, Santosh, do you want to say anything else to wrap up? All right. Looks like Santosh is not connected right now. So thank you all very much for attending. I very much appreciate doing this, and perhaps we could do something like this again sometime. Like I said, if you have any questions, please let us know. Thank you, and have a good evening.
Yeah, that's right. This is a plot of Crystal Violet that we were just talking about. And what commonly teachers want to do with this is do calculated columns.
Yeah, and this is one of the few times when we do anything with spectroscopy versus time. So that's always another, first switching into events with entry mode, and then going back, because we usually do that for either a colorimeter or a spectrometer, and then going back in with kinetics is sort of like, to me, this is not the way you're supposed to use a colorimeter. But
right.
In this experiment, and there's a lot more timing involved in this one.
Yeah, this one does take a little bit of manipulation, but this is one that's very popular in workshops, is to look at the sorry, I'm getting distracted here. The absorbance versus time versus the let's see what I've got going on here. And so then what you want to do is I see what's happening here. My axis is weird. And then determine the rate of the expression of the reaction in terms of what they call the integrated rate law. And so there's, why my data is like wacky there. I don't know why I did that. Let's go back to one graph. Looked okay at one graph. It just, that's weird. Yeah, let's open that data set again. Were there any questions from anybody?
There was a question about a certificate. Can we get it's a lot of times for continuing ed credits. I assume that's what that is about. So I've asked Santosh to see if we can create something. I'm not sure what the requirements are like. They're a little different from place to place. I know when we go to New Jersey, they have to be in a specific format for the teacher continuing ed credits. So I have a question into Santosh if we could do that for our participants today.
Okay.
Also a question about if you have questions while doing experiments. If you write to chemistry@vernier.com, we can answer questions. Also, Edutech in India, because they're in the same time zone, can usually get to you much more quickly. So Santosh organized today's webinar, and he's quite good about getting back to people, and he also has a team of people that can help get back to you locally. But chemistry@vernier.com, feel free to send us an inquiry. If we need local help, we can always send it back to Edutech. Otherwise, if it's directly about the experiment, we can usually get an answer back to you within, but maybe not as quickly.
Yeah. Yeah.
All right. Well, thanks, Noose. I I think I'm going to get some more caffeine now.
Yeah, well, I think I will too. Yeah, I think I've got some things I need to clean up here before I head
Wow.
out.
So, thank you, Jake. I see Gerard has also joined us in between. So, thank you, Gerard, and thank you, Neil. Thank you for the wonderful session. I think the session was quite informative. If there are any follow-up questions, we'll collate them and send it to you via email. Once the recording is ready, we'll share it with the participants as well. The contact person at Edutech is Rajappa. So I'm sure all of you would have received an email invite from him for the session. So you already have his coordinates. Please feel to reach out to him if you have any queries. We're always here to help you. And until we organize the next session, thank you. Thank you for your time. Thank you for making yourself available for this. We hope to connect with you soon. Thank you, everybody.
Great. All right.
Great.
Well, thanks.
Bye-bye.
This will wrap up today's session. And we will, as I mentioned, we